Hello, I am Isha Saxena, 19 BCE 1057, and I am going to cover the topic of Fermat's and Euler's theorem for my digital assignment 3 for the topic of for the subject blockchain and technology under the guidance of Professor Ganesh R. Introduction and definition. So, Fermat's little theorem is a fundamental theorem in elementary number theory, which helps compute powers of integers modulo prime numbers. It is a special case of Euler's theorem, which the definition of which I will deal with in the following slide, and is important in applications of elementary number theory, including primality testing and public key cryptography. Euler theorem deals with the concept of prime numbers, again, modulus remainder, and congruency. It aims to provide a concept where co-prime numbers can be correlated somehow to provide a value that can be used later as a hash value or for encryption key in cryptography. So both of these theorems, they deal with prime numbers and integers and modulo operations, and both of them play a key important role in the domain of cryptography, which ultimately impacts the technology of blockchain in one way or the other. And both of these theorems are technically interrelated because Fermat's little theorem is just an extension of Euler's theorem. So we'll see how. So first of all, we'll deal with Fermat's little problem and then we'll deal with Euler's theorem. Fermat's theorem, which states that let P be a prime number and A be any integer. Then A to the power P, A is always divisible by P. For given A to the power P, A is always divisible by P. So in modular arithmetic notation, this can be written as A to the power P triple equals A mod B. Let's deal with an example. So 11 is prime. So 2 to the power 11 minus 2 is equals to 2046, which is divisible by 11 by Fermat's little problem. So to brief it up, what Fermat's problem states that A to the power P minus A is always divisible by the exponent P. Proof of the theorem. So in the following slides, we'll see 3 to 4 different ways of how we can prove this theorem. So using Euler's theorem, let phi be Euler's torsion function. Euler's theorem says that A to the power phi n is equals to 1 mod n, where A and n are co-prime. So let n be a prime number P, then phi P kept into the function of phi is equals to P minus 1. So A raised to the power P minus 1 is equivalent to 1 mod P for any A co-prime to P. In this case, multiplying both sides by A gives A to the power P is equivalent to A mod B, which is the final version of Fermat's little theorem. So this is one proof. On the other hand, if A is not co-prime to P, then in this case, both A to the power P and A are congruent to 0 mod P. So A to the power P is equivalent to A mod P here as well. Let's move ahead. The second proof is by induction. First, we will show that the theorem is true for all positive integers A by induction. The base case when A is 1 is obviously true since 1 to the power P is equivalent to 1 mod P. For the inductive hypothesis, assume that A to the power P is equivalent to A mod P for a certain integer A. The goal is to show that A plus 1 whole raised to power P is equivalent to A plus 1 mod P. So by the binomial theorem, we have a plus 1 whole raised to power p equivalent to a to the power p plus p1 a to the power p minus 1 plus matrix of p2 a to the power p minus 2 and so on. But for 1 less than equal to k less than equal to p minus 1, because p line p not but p line k not, but p is not equivalent to p minus k. So the middle term vanishes mod p. So a plus 1 whole raised to power p is equivalent to a to the power p plus 1 mod p. So by substituting all of that by the inductive hypothesis, we get the final result. So the result holds for all positive a by induction. But every integer is congruent mod p to a positive integer. So the result holds for every integer. We can prove the same using Lagrange's theorem. So as above, the other case is trivial. The set of power of A forms a subgroup. Its size or order is the multiplicative order of A. So if it is x greater than 0, the subgroup consists of the x elements from 1 to a to the power x minus 1. So by Lagrange's theorem, x divides the order of z, the set z, which is p minus 1. So xy is equals to p minus 1 for some integer y. Then a to the power p minus 1 is equivalent to a raised to power xy is equivalent to a raised to x, a whole raised to power y, which is equivalent to 1 to the power y, which is equivalent to 1 mod p. What is the application of this theorem? So Fermat's little theorem is a fundamental theorem in elementary number theory, which provides compute powers of integers modulo prime numbers that we saw earlier. It is a specific case of Euler's theorem and is essential in applications of elementary number theory, such as primality testing and public key cryptography. So the examples of application and the in-depth explanation of public key cryptography we'll see after we've seen the Euler's theorem. So Euler's theorem, it states that if there are two co-prime numbers, let's say p and q, then p raised to phi q is equivalent to 1 mod q, where phi is the Euler-Toshan function. The simplified equation for the above equation is p raised to the function of phi q mod q is equivalent to 1 mod q. So now the definition. Euler theorem deals with the concept of prime numbers, modulus remainder, and congruency. It aims to provide a concept where co-prime numbers can be correlated somehow to provide a value that can be used later as a hash value or for encryption key in cryptography. So Euler's theorem states that if GCD a comma n is equivalent to 1, then a raised to the function of Euler is equivalent to 1 mod n. Here, phi n is Euler's Toshan function. The number of integers is 1 to n minus 1, which are relatively prime to n. When n is prime, this theorem is just Fermat's little theorem. So let us take an example. Let us take two numbers, 15 and 7, which are relatively prime, as they are co-prime to each other. Let p is equals to 15 and q be 7. So 15 raised to the function of 7 mod 7 is equivalent to 1 mod 7, which is equivalent to 1. Since 1 mod 7 is 1, that is y mentioned in the above image. Now let's verify the LHS. Phi 7 is 6, which transforms the LHS of the above equation as shown below, which is 50 to the power 6 mod 7, where 15 to the power 6 is 11390625. So 11390665 mod 7 is 1. As it comes 1, and also 1 mod 7 is 1, therefore LHS is equals to RHS, therefore the theorem is verified. Now let us see about the applications. Fermat's little theorem says that if P is prime and A is not multiple of P, then A to the power P minus 1 is equals to 1 mod P. And Euler's generalization of Fermat's little theorem says that if A is relatively prime to M, then A raised to the function of phi M is equivalent to 1 mod M, where phi is Euler's so-called totient function. This function counts the number of positive integers less than m and relatively prime to m. For a prime number p, phi p is equivalent to p minus 1. And to Euler's theorem generalizes Fermat's theorem. So Euler's totient function is multiplicative. That is, if a and b are relatively prime, then phi ab is equivalent to phi a into phi b. So we will need this fact in the following slides. One of the major applications of these two algorithms and the main domain for blockchain is RSA encryption. The original RSA public key cryptography algorithm was a clever use of Euler's theorem. Search for two enormous prime numbers, P and Q. Keep P and Q private, but make N is equals to PQ public. Pick a private key D and solve for a public key E such that DE is 1 mod phi n. Since you know P and Q, you can compute phi n equivalent to P minus 1 into Q minus 1. And so you can compute the public key E. But someone who doesn't know P and Q, but only their product N, will have a hard time solving for D from knowing E. Or at least that's the hope. Being able to factor n is sufficient to break the encryption scheme, but it's not logically necessary. Maybe recovering private keys is much easier than factoring, though that doesn't seem to be the case. So where does Euler come in? Someone who has your public key E and wants to send you a message M computes m to the power E mod n and sends you the result. Now, because you know D, you can take the encrypted message ME and compute m to the power E whole raised to the power T is equals to m to the power phi n is equals to m mod n. It's by Euler's theorem. This is the basic idea of RSA encryption, but there are many practical details to implement the RSA algorithm well. For example, you don't want P and Q to be primes that make PQ easier than usual to factor. So you want to use safe primes so that the encryption or rather the decryption of public and private key becomes harder for someone who wants to hack or wants to uh, retard the security. So this was all about Euler's and Fermat's little problem. I hope I was able to justify both the algorithms and state a clear use of this in the blockchain domain, which is basically used for cryptography and basically used for securing transactions. Thank you.